Hello, problem solvers. This is a problem about integers. So the category will be number theory, and so we want to find all numbers k that can be expressed as a sum of two relatively prime numbers. Relatively prime means no common factor, or the GCD is 1. Okay. Please have a try. First of all, let me just say something general about these problems. Usually, a problem can be difficult in several ways. Maybe it requires some knowledge that some, let's say, advanced knowledge that maybe not everyone knows. Maybe you need to use Fermat's little theorem, which not every high schoolers know. Okay. Maybe it requires some proof technique, like proof by contradiction. Those are the harder kind. Maybe it's difficult just because you don't know where to start. So this problem is of the third kind. It looks just general, okay, but it's not hard. Okay, this problem is not hard. It's just it looks like there's no obvious line of attack. Okay, but actually, if you just try it out, so the trouble is that, let's say you try to experiment with small numbers, right? You try to find, let's say, 10. Okay, maybe 10 is not a good choice. Maybe 11. Okay, 11 is 2 plus 9. Okay, it is also 3 plus 8, and both are relatively primes, right? So actually there are more than one way you can do this. Okay, for some numbers there is just one way. For some numbers there is no solution, not possible. But some numbers there are more than one way, so it's quite hard to pinpoint which one to apply to all. But with more experimentation, you should be able to arrive at the solution. So please have a go before continuing. The answer is that it's possible for any k that is not in the set 2, 3, 4, 6. In other words, 5 and anything above 7 or above is possible. So of course 5 is possible, right? 5 is, you can just check. 5 is 2 plus 3. And if you just try a few more odd numbers, you can easily see that, right? You just split into the half. Okay, the middle two numbers, right? So that is the claim 1. That is our claim 1, which is easy. You can easily prove. Okay, for any odd k bigger than 5. Okay, it's possible. So for example, so the proof goes like this. Okay, let's say k is an odd at least 5. Then we can say k is 2n plus 1, where n is at least 2. Then the numbers n and n plus 1 are relatively prime, and k equals n plus 1. So these two numbers are relatively prime, and they add up to k. And so we just show that for any odd numbers this is possible. So that is the easy part. So what about even numbers like 10? So 10 would be 3 plus 7, right? But 12 is a good example. If you just try 12, okay, 1 doesn't work, we cannot use 1. 2 and 10, not working. 3 and 9, not working. 4 and 6, not working. 5 and 7, sorry, 4 and 8. That's the only pair that works for 12. Okay. So you see, for 12, it's kind of like we divide in the middle and then subtract 1 and plus 1, and that works. It's kind of like this. We divide in the middle. Right, just look at the middle numbers. For 12 works. But for 10, it didn't work. Okay. For 10, the middle number will be 5, 5, doesn't work. 4, 6, doesn't work. It only works for 3, 7. Okay, so we have some discrepancy here for these two even numbers. And the natural way to attack will be divide into cases. So you see, this is 2 times a prime, 2 times an odd number. Okay. 10 is 2 times an odd number. This is 4 times an odd number, and they are different. So let's have 2 more cases to deal with them separately. So let's do the easy case first. Let's do the case for 12. Okay, if you have a number k that is divisible by 4, okay, that is not 4. Okay, I should say k should be at least, yeah. So k is bigger than 4. Okay. K is 4 doesn't work, right? 4 doesn't work. You can try, but for any k divisible by 4, it works. So, well, the proof is just like here. Just replace numbers with alphabets. So let's say k equals 2 times 2n. Okay, where n is at least 2. Then consider the numbers 2n minus 1 and 2n plus 1. The GCD is 1, right? Because well, the proof goes like this. This is one of the facts about numbers, okay, or about GCD. If you have GCD of 2 numbers, the GCD is actually equal to their difference. Okay, you can do something like this. Okay, let's say b is bigger than a in this case. Okay, so if you just use this property, you see that GCD 2n minus 1 is just this minus this, which is 2. But this is an odd number. It has no relatively prime to even to 2. So GCD is 1. Okay, and obviously they add up to 4n. Oops. Okay, so it works for this case, and the remaining case is just 10, the 10 case, and we can similarly replace numbers with alphabets. And this is our third case. Okay, for any k that is bigger than 6, that is divisible by 2 but not by 4, it's possible. Like 6, we know, you can check, it's not possible. So it's like 10. Think of 10. Okay, how does it work? Well, we cannot just use the middle. 5, 5 doesn't work, right? But if you just jump by 2, okay, 5 becomes 3, 5 becomes 7, and these will work. Okay, so let me show you. So let's say k is 2 times m. Let's say 2 times 2m plus 1. Okay, so that this is an odd number. Okay, if you divide by half, you get 2m plus 1, 2m plus 1, and it didn't work, right? Because they are the same. It's like 5 and 5. But as I said, if you decrease by 2, increase by 2, consider the next pair of odd numbers. This will work. So obviously, k equals the sum of these two numbers. Okay, this is 4n plus 2, this is 4n plus 2, and moreover, the GCD is 1 because you can use this property again. So GCD of this minus this, you get 4, but this is an odd number, so it has no common factor with 4, and so these are relatively prime and they sum to k, and that's the end. We have for each case, right, we solve for odd numbers, we show that it's possible. For numbers divisible by 4, we show that it's possible. For numbers not divisible by 4 but even, that's possible as well. So we have divided the numbers into 3 cases, and it worked. So that is the end of this solution. If you reflect on what I said at the beginning, some problems are difficult because there seems to be no obvious line of attack. Well, you see, at the end, there is really no obvious line of attack because there are 3 lines of attack, right? Which is the odd case, which is the divisible by 4 case, and divisible by 2 case, right? So that's why this problem, it seems to us no obvious line of attack, because there are actually several lines you have to attack. Okay, so whenever it looks quite open, you can consider divide and conquer, right? Think of some cases to solve. So that's it for this problem, and let's end by giving it a difficulty score. I would say this is difficulty 3, and the character for this would be cute and not easy to beat. Thank you for watching.